Hello everyone. In this video, we are going to talk about the programming language used for Denso robots. If you have seen some of my videos, especially the short videos, you see that I have used these Denso robots that we have in our lab here, the Scera or the 60OF1, and I have done different tasks for them. Okay, so with the Scera, I did writing. I can attach a LiDAR here and map the environment, which is, by the way, going to be my next video. With the 60OF, I can attach a marker to it. So in our lab, we have a pneumatic gripper here. And with that pneumatic gripper, basically, I have done different tasks, including pick and place, including writing cursive letters and so on. And these robots, they can also, if you want, you can attach a camera to them and you can do vision, which is going to be another one of my future videos. And there are lots of different tasks that you can do. So as promised, in one of my future videos, I show you how to use a 2D LiDAR and map the surrounding of the Scera. And hopefully, probably I show you something about a vision. Now, the main thing is, how do you program these robots? Because when you program them, you don't do it in MATLAB or Python. You do it in a language called PAC. And PAC means Programmable Automation Controller, which is used in Denso robots. And it's a language specialized for industrial automation and robot programming. So we want to know how to basically write any code in this language. We want to briefly learn about this language. The software that you'll see in the next video I'm going to use for the Scera or this 60OF, as I said, the software is called the WinCaps, and the last version is WinCaps 3, which you can use to program the robot offline. You can do simulations, I/O configurations, and so on. What I will do is online programming next time, offline programming. And you're going to see how I do it. So we create the code and then we transfer it to the robot and then compile it on the robot and let it run. Okay. So what is the structure of PAC? If you want to see a PAC language, what kind of structure would you see? So if I want to do a simple pick and place job, right? Let's say this pneumatic gripper is attached. If I want to go to a point defined by the position of the point defined by P100 variable and pick it up, go to another point, go down, let's say with the Scera or 60OF, and now go to another place, which is the place point defined by the variable P101 and put the part there and go back, right? So if I want to do something, the structure of the code will be something like this. This is the kind of code that you might see. What is it? The first line could be some comment or something if you want, and you can insert comment anywhere else along the code. But if you see any line starting with a single quotation mark, or you see a line starting with a semicolon, that is a comment line. Okay, so here. So any line starting with a single, not double quotation. Double quotations are for strings. If it's with a single quotation or a semicolon, okay, if you see anything like that, anything after that is considered a comment, and the processor is not going to care about them, okay? So the first line that you start is the name or title of your program. It starts with the word program and it's all in caps. And then you provide the name or the title of your program. Okay, so that's the first thing you do. And I mentioned that for you over here. Then you write all of your commands. And at the end of your program, you end it with the keyword end. Now, one thing that we need to care about the end is, the end means what? The end means the end of motion in this program. It doesn't necessarily mean the end of the program itself. And you might say, what are you talking about? Well, if you have subroutines that the main program is using, if there are subroutines, the subroutines are typically put after the main program. So if you have any subroutine, you're going to see they're going to go below the main program. So end doesn't mean the whole code is ended. It means the motion, anything that is done in the main program is ended. Okay, so it separates your main routine from the subroutines. Okay, so that is the first thing that you need to consider. One other thing that you see over here is that the commands, you do not need to terminate them with a semicolon. Like you do in MATLAB, you end them with a semicolon, right? If you want to suppress the output, you don't need to do that. Or in C, if you remember, so in C, as I said, you also terminate the commands with a semicolon, but not in PAC. You don't need to do that like Python. Like Python doesn't have semicolon. That's the same thing for PAC. Another thing is indentation. MATLAB and C, or C++, you're encouraged to indent it, but you don't have to. In Python, you do have to. Okay, you don't indent the program, you're gonna get error. What about the PAC? In PAC, the programs do not need to be indented. If they are indented, that's really good and it's encouraged, but you don't have to do that. Okay, so these are the things I just told you. I just added this part for you. Okay, now what are the things you do? The first thing you do, you start, if there is motion involved, you want to start the robot and a bunch of things that needs to be done at the start, and we'll talk about them. The command that you start with is called take arm. So you typically, your motions of the robot start with take arm. So what is take arm? If you read the manual of PAC language, it says it gets an arm group. Well, what does that mean? If you want to plain it in a simpler language, is when you start this command, the speed of the program, the acceleration and deceleration of the motions and joints will be set to 100%. Okay? And if there is any tool coordinate that needs to be attached, this is gonna take care of that too. So this is an initial startup setting of some parameters and so on, specifically speeds and acceleration, decelerations, and considering that there was a tool coordinate that needs to be considered. Okay. So this is mandatory, and you don't need to pass to it necessarily any input arguments, although you can, but this is typically the first thing you do. And at the end of the program, you release the control and the resources back to the robot by this command like give arm. This is like in MATLAB when you create an object, right? And at the end you delete it or release it. This is kind of similar thing. So give arm releases the control of the robot arm so other tasks can use it. So make sure you start with take arm and end with give arm. And then in between you have the motions. So what would you do? Let's say you want to pick some part from here, right? You have a part from here, you want to pick it, go up, and then drop it here. So the first thing you do most of the time is when you want to go and pick a part, you do not directly go to the part from wherever you are. So let's say your end effector is here, you're not going to go like this, directly at it. You typically go above the point and then you descend vertically down on the part, especially for a Scera that all it can do is to go up and down. Okay, it cannot go at angle. It doesn't have theta x and theta y. It only has a theta z. But many other times you do that as well, because if the object is a little bit big and so on, you might hit it. Or there might be some obstacles on the way that you would hit. And only above the object is clear. Let's say the object is inside the bin or something, right? So if the object is inside the bin, guess what? And this bin is quite a bit big, like this. You cannot just directly go toward the object from wherever you are. You first go above it and then go down. Okay? So this is very, very common to do a good job. And that is done with the approach command. So approach means what? Means you don't need to go to the point. Instead, you go so much above the point. So it's a relative command. You ask your robot end effector to go so many units above that position. So you say go to point P100 and not exactly there, but 75 mils, and this is in millimeters, above the object. So it's a relative measurement with respect to the target point, and do it with the speed of 100%. Okay, so you do an approach command, then once you are there, you do a move command. Now you want to straight perfectly go down to the point, so you do a move command and move. The point that you give it is exactly in the absolute coordinates. So you say now you move from wherever you are to the point P100 and go on a line in the workspace. So you have to go straight on a line, make sure you are exactly there, and at the speed of 100, go perfectly down to the point. Then here you have to add some extra commands, which is about opening the gripper or closing the gripper. So we'll talk about that later, how to close a gripper or something. Then maybe you want to wait 100 milliseconds. So wait, don't do anything, wait 100 milliseconds. Then depart from this point. Depart again is a relative thing. Depart means from wherever you are in the z direction. Z of what? Z of the end effector. If z of the end effector is like that, in the z of the tool or end effector, move away from this point by 75 mil again. So go back by 75 mil, go back, and with some speed, then go on the top of the next point, 75 unit above it, then go down. Again, here you have to open the gripper, wait, then depart that point, and so on and so forth. Okay, so this is a very simple for a simple task like a pick and place. This is the kind of code that you write to do a simple pick and place. You do a bunch of movement commands like approach, move, and depart. You might need to sometimes put some delay. You need to open and close, which we'll talk about it. And all of them happens between a take arm and give arm. And finally, you end the major or the main program. Okay? So this is the overall structure of the PAC language. Now, there are a bunch of things that we need to know, like more about the approach command, about the move command, about the depart command, how to declare variables, right? And confirmation of whether you reach the point or not. You can move on splines, you can move in the joint space, you can move in the Cartesian space, right? There are all sorts of things that we need to talk about, how to set up the speed and acceleration, delay, how to do if then else, switch, how to do for loop, while loop, how to set up input outputs and send something to them, sound the buzzer, if there are math functions, if you want to create, if there are built-in constants, if you want to define a constant or a macro expression, if you want to stop the program, if you want to create a user-defined function, a subroutine, if you want to jump to some part of the program, and so on. So these are all of the things that I want to discuss with you in this video. And then in the next video, we're going to see some of these I will use to perform a mapping of the environment, because I want to use these and I want to talk a little bit about mapping. Okay, if you want to use a LiDAR and mapping, there are a few intricacies that we need to talk about. So the first thing is that you saw here, these variables P100, P101, these are the variables that show the location of the point, correct? In the robot base frame, how do you define a variable in the PAC language in the first place? So one thing important about the PAC language is, this is like C or Python, is a typed language. You have to tell the processor what kind of variable you are using. Is it integer? Is it double? Is it a string? Whatever it is, you have to tell it. So if you want to define an integer, the command you can use is defint. This is to define an integer, and then you say the variable is f1. Or this is a double variable, double precision, you say def double. There are commands for def single, for string, and so on. And if you want to know more about all of these different commands, so here my goal is not to go over each and every one of the commands in this language because it takes forever, but there is this document here which you can easily download from the internet. It's free and available, provided by the Denso company. Okay, so this is the programmer's manual, and this is a really good document. You see it's like 700 pages, and you can go here and see all of the commands in alphabetic list, and when you click on each one of these hyperlinks, it takes you to that specific command. So if you want to use, for instance, def int, right, you go, you see define an integer, you click there, and it takes you and shows you the syntax and some examples for how to use it. Okay, so you can do that here, and you can use it, as I said. Okay, and if you want, I can upload this on the Google Drive, and I can give you a download link for it. If you want to directly download it from under video description, I can also give you that one as well. So you see here, I use def int, and I define the command, the variable. I can also, if I want, I can also assign a number to that variable right in the same line that I define it. So if I say def int f1 and then this is equal to 6, guess what? I can do that here. Or this one is, I don't know, 1.245. I can do that. Okay, so you don't need to do it in two separate lines. First, in the first line, say def int f1, and the second line, say f1 equals 6. You can do both of that. And for the robots, one of the things that is very important is, as I said, locations of the waypoints, location of the points to reach to. And these locations can either be defined in the joint space, or they can be defined in the work space or Cartesian space. If you want to define them, define joint variable, there is also a command for defining joint, def joint, JNT, you can do. Or if you want to define it, first of all, if that variable is an array, so if you are trying to define an array, because the positions in the joint or workspace is definitely an array, correct? You either have 6 numbers for position and orientation in the workspace. By the way, speaking of which, in Denso, like for instance the 60OF Denso, in the Cartesian space, the position of any point is defined by x, y, and z, and the orientation of the end effector at that point is defined by absolute theta x, absolute theta y, absolute theta z. Okay, and I'll show you. But if you want to, in Denso, define the end effector pose at any point, remember that the 3 angles that you use are absolute angles. They are not Euler angles. Okay, so that's another thing you have to pay attention to. But if you want to define it in the joint space, well, for this, then you have 6 Q values, right? Q1, Q2, all the way to Q6, or if it's the Scala, Q1 to Q4. So it's clearly an array that you need to define. Now, how would you define an array in this language? You have to start with the keyword dim, which is for dimension. So dim means whatever variable you define afterwards, that's an array or a matrix in general. Okay? So pay attention that this is how you define an array. You give it a name, and then the first thing you do after that, inside parentheses, you say how many of this array do you have. Because as I said, in general, it's like a matrix where each row of that is an array of a specific type. But how many of these arrays are you putting together as a matrix? How many waypoints do you have, right? So here, you say 2. I have 2 waypoints that I want to define and call both of them my joint. The first one is this point. The second one is this point. Another thing very, very important in this language is this language, the index or indices start from 0, not 1. So they are similar to Python and C, not MATLAB. The indices of anything starts from 0 and not 1. So the fact that it has dimension 2 means the first element is element 0, the second element is element 1. That is a very common mistake that I see when my students give me the PAC code and I want to debug it and send it to the robot is, for instance, they go here from 0 to 6 and then they say the dimension is 6. That's not true. Because you start from 0, if the last element is 6, your dimension should be 7. Okay, because you have 7 entries, you have 7 points. So this is very common, and I want you to pay attention whenever you are writing a code with a Denso robot. Now, as I said, you can either say this array is some variable in the joint space, it's a Q, or it's some pose like P or X, you might call it, whatever you want to call it. So if it's in the joint space, you say that variable as joint. If it's in the Cartesian space, x, y, z, and angles, then you say as position. Okay, so this way you can tell the processor what kind of variable you are dealing with. And the other thing that you need to pay attention is the way that you put these numbers for each vector, you put them inside parentheses. It's not a bracket. In MATLAB, it is a bracket. In here, it's parentheses. The other thing is between these numbers inside the array, you should separate them by a comma. You cannot have space, like MATLAB allows you to either use comma or space. Here, you cannot do space. If you do something like 22 space 33, you're going to get an error. It says, hey, what are you talking about, the space? Or if you use bracket. They're all mistakes, syntax errors, okay? So pay attention that it's a typed language, indices start from 0, use parentheses, and you separate the numbers by a comma. Otherwise, you're going to have a bunch of errors. Okay, so just going over these motion commands, the approach command that I just mentioned, it is to go above a point, right? Above a location. And when you say above, means in the z-axis, the z of the end effector, which for the Denso robot, it could also be the z of the base frame. And it is going to be a distance relative to that target. So you say approach. Now, this P or L, we'll talk about it. This is the interpolation technique or method. Go and comma, and then you provide the point above which you want to be a distance of F1 up. And then you have a position confirmation at P, which we'll talk about it, and the speed of the motion. Okay? And then why would you do that? As I said, you typically do that so when you want to go down vertically, it is done in a safe way and you don't hit the obstacles, okay? As I showed you, you don't directly go at the object, you go above it and then you safely go down. So this is the approach command. And the thing about this approach is it is done fast. We'll talk a little bit more about it. Then we have the move command. So two things before I move to the talk about the move command. Two things I need to talk about. One is this @ sign something. The other one is this P or L. Okay, so these two, I need to talk about them. But the move command has 3 formats. Approach has approach P and approach L. Move has move P, move L, and move S. So what's the difference? So now it is time to talk about P and L first, and then we go to S. So P means what? P means point to point or joint interpolation, joint to space interpolation, point to point, PTP. What does that mean? Means when I want to go from my current position to this location P1, so this is the current location or current pose, and this is the target pose. How do I interpolate between these 2 points? Because you have to have a bunch of points in between, correct? To follow them. How would you do this path planning? Do you go straight with a line, because line is typically the simplest thing to do? When you do this line, do you do this line in the joint space or do you do it in the worker space? If you do it between the Qs, so you do it on the joint values of the current pose and the joint values of the target pose, if you do that, then that is called the joint space interpolation and move P. So you do this, it is linear in Q space, but as you know, since your forward kinematics equations, which will take you from the Q space to the worker space, these equations, again, if this is current and this is target, these equations are nonlinear. So in the worker space, you might see something like this. Your end effector will not move on a line in the joint in the worker space. It only the only line that you see is between the Q's of the current and the target, not in the worker space. So this is move P, do the interpolation in the Q space. But if, on the other hand, you want to go direct on a direct line between current and target like this, so here you have to calculate these points, and then to find the command Q for them, how much Q you need to command them, from these points you have to apply inverse kinematics to find the command for the encode for the motors, right? So depending on whether you use the built-in forward kinematic functions or inverse, and of course, actually you don't really need forward kinematics for the P2P, because at the end of the day, what you command are the motors. The only thing you can command are the motors. So when you command them in the joint space by forcing the Q's to go to these desired values in between, this forward kinematics is done via the robot. You don't need to do a built-in forward kinematics. This is automatically done through the robot, and in the workspace you see the effect of it. But if you define these points, as I said, in the workspace, and you say, I want to go on a straight line, now you have to use the built-in inverse kinematic function that the robot has, the controller of the robot has, to find the corresponding points for it in the Q space and command your motors to go through these. And again, in the Q space, clearly, although in the worker space it was a line, in the Q space clearly it's not going to be a line because your inverse kinematics equations also non-linear. So if you do it linear in the worker space, you call it L, move L, approach L. If you do it in the like this, in the joint space, you do it like a line, that is P, point to point. Okay? So that is the difference between L and P, which you can see it both for approach and you can see it for the move. Now, when you do the move command, the point, the coordinates that you provide, this is in absolute coordinate frame. Okay, this is the absolute coordinate of the point, and basically it's not a relative distance like here you had with F1. So it directly goes to that point. Okay. Now, you might ask, why would you use move P or move L? What is your preference here? When would you pick move P? When would you pick move L? It depends on the importance of the motion. If you really want a precise straight line motion in the workspace, then your option is definitely move L. Okay, this is very important when you want to make sure that you do a perfect line, and the accuracy in the workspace and the shape of the end effector motion or path does matter. Like when you're inserting, let's say, a bolt in a knot, so you have the knot here and you have the bolt, guess what? You cannot clearly go ahead and when you want to go from this current position to this goal position, the only way you can do it is a straight line. You cannot do any other crazy motion. So in this case, when inserting, sometimes doing a weld bead that is straight, gluing some parts in, as I said, pick and place, many scenarios, you have to do a straight line, and you have to do the control in the interpolation in the what we call continuous path, or CP. Okay? On the other hand, if you don't care how you go from point 1 to point 2, all you care is to do it as fast as possible, and you don't really care too much about the path, like when your end effector is moving in safe zone where there is no obstacle around the end effector or robot and there is no collision, then the P command will allow you to do the job faster. Okay? And this is the advantage of the P, which is point to point, as opposed to L, which is continuous path or CP interpolation. So that's the difference between P and L. Now, move command, so that's also the same between approach P and approach L. They have the same difference, approach P and approach L. Okay? There is one other option with the move command in Denso Robots, and that is move S. What is that? This is when you don't want to move on a straight line in the workspace. You want to move on a spline in the workspace, okay? So let's say you're writing something. Let's say you're writing cursive letters, right? So you want to say, for instance, hello, right? Something like this. Then you are working on a bunch of splines. So each spline is defined by a bunch of control points. It's a smooth curve. And in general, by a combination of spline and straight line, you can literally do anything you want in the workspace. Then move S is going to do that for you. So you can move on arbitrary arc or curve given by spline. All you need to give the robot is the coordinates of these key points of the spline. That's all you need to do. It does the rest of the spline interpolation itself, and it finds the joint values for them in the Q space by inverse kinematics that has built in, and commands the motor to move. Okay? So when you do advanced kind of manipulations like polishing, painting, camera scanning, and so on, and you need complicated shapes in the workspace, you can use move S. Now, how would you command move S? So we have seen move L and P. As I said, there is some @ sign that I need to talk about, and I will. You need a target point, and you can control the speed. But what about the spline? How would you move on a spline? The first thing you do is, there are a bunch of spline variables that are available in the memories of Denso Robots, like spline 1, spline 2, spline 3. The first thing you do, you clean the memory of them. You clear the memory of these splines. What does that mean? Means if for spline number 1, I stored in it a bunch of points, a bunch of these key points for one previous task, first, I clean all of those points from this spline 1, so it becomes empty. Then I define the new points for it, and then I use the move S command to move along this spline number 1. How? The first, I clean up, as I said, all of the previous point on spline 1. How? I use the command clear spline point, so it clears all of the points from spline. Which spline? Spline number 1. Okay, so it cleans up spline number 1. Then what? Then you define the new points for spline. How? You use the command set spline point. So for spline number 1, go ahead and give it some new points. Which new points? This point here, called spline 1 element 0, spline 1 element 1. So all of these control points are now going to be defined by this vector spline 1, which has so many components. And the way that you define it is exactly like this or like this. Okay? So you define it as a vector. Once you define all of the points for that spline number 1, and spline number 1 is fully defined, now you say, hey, go ahead and move on spline. Which spline? Again, spline number 1. Move on spline number 1 from one control point to the next, to the next, to the next, and do it with the speed of 20%. Okay, that's all you need to do. That will start from the first point on this spline and gradually goes to next, and does it. Then you can repeat the same thing for spline number 2 and spline number 3 and 4 and so on. And remember that when you use splines, if there is a sharp corner, you have to switch the spline. So here I can say this is one spline, but because here I have a sharp corner, I'm not going to call this flat line to be a part of that spline. So if this is spline 1, here I have to terminate it. If I start it here and end it here, this is going to be the start of the next spline. This is going to be the end of next one. And then I come here, start this one, and then I gonna maybe end it this one. So because here I have the sharp corners, I have to switch to a new spline. Otherwise, you will not get sharp intersections because splines are meant to be smooth. Every point has derivatives. So pay attention to that one. So we have seen approach and move. So now it's time to talk about this @ sign thing. What is this @ sign? This is called confirming position. Okay? So when you command your joint to go to somewhere, how would you know that it has actually reached there, right? Because you command your motors to get to some point and you want your cues to converge to some cue desired. How would you make sure this has happened? There are 3 ways that you ask your robot to check. One is called pass motion, which is @ sign P. One is called end motion, @ sign a number. And the last one is called encoder value check motion, or @ sign E. E stands for encoder, P stands for pass, and that is just a number. What are these? Okay, how do we ask? In the pass one, @ sign P, which is like the weakest way you can check, all that matters is your end effector just past the vicinity of your target point. So what do I say here? Look, I say program something, take arm, move P at P to P2. What does it mean? Means from my current position, which is P1, I want you to pass close to P2. You don't even need to end up exactly at P2. As long as you are in the vicinity of it, as long as you pass close to it, this is good enough for me. And there are some built-in thresholds for defining the vicinity in the controller of the robot. Now, sometimes you want to determine that threshold. You want to say what threshold, what does vicinity mean. You don't leave it up to the robot. You want to tell the size of that vicinity, and that's where you use @ sign number. So here I say, no, I want you to go at, for instance, instead of at 0, let's say at R instead, and R is a number, so go. And actually, yeah, that does not exactly correspond to this. Here it has to be move, or yeah, actually, no, that's right. Move L is fine. So go on a straight line, but when you want to get close to point P2, be around it inside a radius of R. So here the radius of the circle is R. And you can make R as small as possible, even 0, which means literally add it, okay, to get there. Good. And typically this radius, although you are determining that, but that depends on the servo itself too. Okay, so the resolution of the servo also determines how small this R is going to be. And the way it does it is by checking the command value of the servo to check whether the command value of the servo meets the destination position. So it does not look at the encoder values. It just looks at the input of the servo, the command of the servo. Does it match the ones that it should be? Okay, so if the U of the servo is equal to the U desired, it says, guess what? I'm good to go. In encoder, now you don't just say because the input was whatever it should be, it means the output is also whatever it should be. You don't trust that. You go and read the encoder. So now you really look whether Q is equal to Q desired or not. You read the encoder. If it is, then you say yes. Now the way you do it is with @e. So here you say, I want you to get to P2. This E is encoder. Also, you can interpret it as exact. I want you to be exactly at P2 and confirm that for me by reading the encoder values. Okay? So the way that you do it is any of these, and @e is typically the best one because it's the most accurate. It's like a closed loop kind of feedback. It's not real closed loop because you are really looking at cues. You are not looking in the workspace. If you want to do the feedback with workspace, you have to have a way to exactly determine the position of the end effector and orientation of it, which is not a trivial task. So you can assume that your robot is very rigid and there is not too much gear backlash or anything. So if your cues are equal to Q desired, this kind of tell you that X, the pose of the robot or end effector, is also the X desired. This only happens if the robot is very rigid and there is not too much gear backlash or something. Okay, then you can say, well, yes, my robot is very repeatable and it can really fulfill the command. So now, why would you pick one versus the other? One is, of course, the accuracy. @e is the best one, then @r, and then the loosest one is @p. But there is one more thing about this confirming of the position. What is that? You might say, well, if @e is the best one, why do I even have @p and @number, right? That's the best one. Let's use that all the time. Well, there is one thing that you need to know. The @p1, the one that just passes close to it, is the fastest one. So if you want to get to somewhere and very close to it, vicinity of it, the fastest way possible, you ask @p to be checked. The @number is going to be slower and the encoder one is going to be the slowest. Why? Because the way that the motors are commanded to start from, let's say, rest, accelerate, and then decelerate and stop at the goal position, the profile of the speed command is different for these three types of checks. In the pass motion, this is what happens. You start, let's say, from a stationary position, from rest, you accelerate, then what? Then you go for a constant speed, and then what? Then you decelerate. And you see that the acceleration and deceleration are done over a short time. Most of it is done with some maximum speed. Okay? But if you look at the one that is @number, the way that you do it, if you want to go from P1 to P2 to P3, you first go from P1, speed up, accelerate, go at constant speed. When you reach to P2, you temporarily come to stop. Then at P2, you speed up again, you accelerate, and then you decelerate and stop at P3. Do you see that? So when you get at P2, you stop. And because of that, it takes more time to go from P1 to P2 to P3. But here, if you look at it, at P2, you do not stop. You keep going with the same speed. There is no stop over here. You keep going. So these two profiles that you had here at two separate profiles for going from P1 to P2 and then P2 to P3, they are two non-overlapping profiles, but in case of at P, you can see that they have so much overlap that literally this stopping region is all eliminated. And in P3, at E, not only you stop, you wait a little bit. So there is some small region of time for which you completely stop and not move, this region. And this is to read the encoders and make sure that the encoders are giving you what should be giving you at P2 before you move to P3. So here you spend even a little bit more time, and so the time of this is bigger than that and is bigger than this. So it depends on how important it is for you reaching this point P2. Okay? How much do you want to check? What profiles, what the speed profiles you want to use, that is going to determine. Okay, so I guess I talked about all of that for you. Now we need to talk about the depart command. Depart command is also a relative distance from the current point, which you don't need to specify, so your end effector, wherever it is, in the z-axis, the end effector z-axis, move away from your current point by a distance, which is given in millimeters and with so much of speed. And again, this depart could be P or L, right? So you can have depart P or depart L. Now you saw that in these commands, I set the speed. So let's talk a little bit about the speed of the robot. How would you change the speed? Not only that, you can also change the acceleration and deceleration of the robot. How would you do that? Well, you can basically just in the beginning of your code, if you want, you can simply say, hey, I want speed to be 30, and 30 means 30%. Or I want accel to be 50% of its max. I want deceleration to be 25% of its max. Okay? And by the way, they are all capital letters, so if you want to write it, it has to be like this. So one way is to do it globally in the beginning of your code. Then all of these commands that you had, move, approach, depart, you don't need to provide the speed for them. They all will follow the speed. This speed in move, approach, and depart is an optional part of the command. You don't have to have it. If in the beginning you already set it up in your program, you do it now for all of them. But if you want to do them at different speeds, so move at the different, approach at the different, then guess what? You can do it in the command instead of do it globally in the beginning. And of course, you know, acceleration is when you are going up and deceleration is when you are going down. So this is accel, right? This is decel. And here, this constant is your speed that you can have. Okay, so you can set those. Now, one other thing that you need to pay attention is if you looked at dependent of these robots, they have a button on the right side that is called the speed. Let me show you a picture of that. So this is the picture of dependent, and this is this button. Look here. If you click on that, and typically they have a knob here, and as you turn this knob, the speed is going to change from 0 to 100%. Okay? So you might say, do I control this physical button speed? No. That speed that you control by that button is called the external speed. Okay? Seems like there is a typo here. This should be external. That one is the external speed that you're controlling by the knob. Okay? That external speed is what you control here. But the internal speed is the one that you control in the code. Okay? This one is called internal speed. And the actual speed that you see from the robot is the product of the two. Okay? So if your internal speed is 50% and let's say this external speed is 20%, your actual speed is simply going to be just 10%. So if you want the robot to go as fast as possible, you have to put both of these in the code and on the hardware at 100%. And you don't really want to do that because the robot goes like extremely crazy fast. And if the robot is not bolted very hard down to the table and the table is not heavy, it easily shakes and moves the table and could be dangerous. So I don't recommend that. So this is setting up the speed, acceleration, and deceleration globally in the program. What else? If you want to do any delay in the program and you want to delay going from one line to the next line, you can of course use the command delay, and the number that you provide right after that with the space is definitely in milliseconds. What else? If you want to specify a condition, if, else, and end, the structure is like this. If some condition, do some command. Else if some condition, then, and each one of them has a then. Else if some other condition, then do something else do something else, and if, and there is a space here. Okay, so this is the structure. If then, else if then, else, and then end of if, and if. Okay, this is the structure, and in between you can have different commands. So this is if you want to do if else, you want to provide a condition. Now, is that the only condition that you can do? No, you can also do switch, and I show you switch in one of my next set of commands. I show you how to do a switch as well. But if else is of course the most powerful one. What about loops? If you want to do a for loop or a while loop, how would you do that? Well, for a for loop, the command is called for next. So you say for variable equals initial value to what? The final value, and then step 2. Okay, so this is your initial value, this is your final value, this is your increment or decrement, and this is the loop counter or the loop variable. You perform some commands and then you say next, and also have to add that loop variable after next. So this is the structure of for loop. What about while loop? So you say while some condition, do some command, and then end of while. Now instead of say while end, you just simply say W end. That means the end of while. Okay, and this is a while loop. So for loop and while loop. What else? How about IOs? So if you want to define some specific pin, right, as input or output, or set them and reset them, which means turn them on and off and so on, what can you do? So let's take a look here. I say define two integers, li1 and li2. Then these are just integers. Now I want to define a input or output pin. Okay, I say def IO. This is to define an input output basically pin. Go ahead and on port 220, okay, declare this variable sample or samp1 as integer type variable. Okay, so you're gonna, what you are going to define this variable samp as integer. That is gonna be what you are gonna be sending out or reading in from pin 220 or port 220, and the variable that you read or write is an integer. Now what would you say? You say in read for me at that variable samp1 the li1. So read whatever coming out of that port 220 and assign it to the variable li1. Then what? Go to port 240 and what? The port data, the data that is in port 240, assign it to pin, assign it to the variable li2 in. You see here I'm reading the data in from my ports, whether that port is 240, which I already defined by a variable, or I did it inside the bracket to tell it which port it is. Or no, now I want to send data out from the computer to those ports. So I say go to that port 220 and this li1, assign it to that variable and send that data out. Or that li2, assign it to the port 240 and send it out. Okay, so using def.io in and out commands, we can easily define pins and send the data out or read them in, and the IO command can also be used to define the pin number as well, or port number. Now, if you want to set a specific pin number or port number to 0 or 1, on or off, you can use the command set and reset. So if you say go to pin IO1 and set it, means turn it on, or you reset it, turn it off. Now, when is any of these useful? This is good. These commands are good for pick and place. Like where? Like when you want to open or close the gripper. Because if the gripper, if this port is attached to the pneumatic gripper, to the cylinder, right? So this is your pneumatic cylinder. Guess what? When you send that command on or off, you are going to extend it or you are going to retract it, and that could correspond to your end effector gripper to either be opened or it could be closed. Okay, so when you do these kind of binary actions, on and off, open and close, the set and reset commands are the kind of commands that you want to use. Sometimes you want the robot to make a noise, a sound, so it, for instance, alert the user or inform the user about some kind of action that is happening. You see, when in some cars, right, like Ford cars, when you back up, you put the car in rear, it starts beeping, beep, beep. So that could be something in robots too. For instance, when the robot is moving apart between station 1 and station 2, you want this robot to make beeping to alert the people that the robot is in motion, don't come close to get hit. That's where you use the command buzzer and you provide in milliseconds the time it needs to buzz, okay? Do we have math functions? Yes, you have a big library of them. You have exponential function, min and max. You have power function. So this is, if you say power of A and B, it's A to the B, okay? So that's the power of A and B. Then you have log, which is natural log. You have log 10. You have random numbers. You have sine function. Okay. You have a square root. You have distance, which is like the norm, the 2 norm. You have converting the degrees into radians. You have absolute value, you have trigonometry function, sine, cosine, tangent, you have inverse one, and you even have arctangent 2 of x and y. Okay, so all of them are available. Do you have built-in constants? Yes, on and off, true and false, and the number pi. They are all available, so we can directly use pi. How? Let me show you one example here. So let's say you want to define an expression macro. This is kind of like an inline function or anonymous function that we have in MATLAB or Python. How would you do that? Here, you have to use the keyword define and the @ sign. And you say, I want to define this kind of anonymous function or expression macro, M area, which the input of it, the input argument is radius. And what is the output of it? The output of it is pi times power of radius to the 2. So basically, this is like pi r squared. So I give it a radius, it gives me the area of the circle. Okay? And anytime you want, you can call this M area anywhere in your code, pass it a radius, and assign the result of this to a variable. Okay, so now this M area acts like, as I said, an anonymous function, which in here we call it expression macro. Or what? Or you can define another function called name. And this one basically can define a constant for you, a string constant. What is that? That is Denso corporation. And you see here, this double quotation marks means that variable is a string. So when I say S1 equals name, what does it do? It assigns this string Denso corporation, it assigns it to, basically because it's name, it is going to assign it to variable S1. So S1 becomes Denso corporation. Okay, so this is defining constant or variables through macro type functions, right, or anonymous functions using the define. Or if it's constant, then you can just say constant. You don't need to even call it the macro. What about stopping or suspending the program at any point? And also, as I promised you, what if you want to do a switch statement instead of if then else? If you want to do conditions based on switch, how would you do that? And how can you stop or suspend the program? Okay, so I want to show all three of them to you in one place. So here you use the select case. So here it's not called switch case, it is actually called select case. In other programming languages, we call them the switch case, but here we call them what? We call them select case. So we say select case index, means look at the variable index, and based on the value of that index, go and do one of these operations. What? If that index equals 0, go ahead and stop the program. Stop means completely stop the program, okay? So the program will be fully stopped. You have to start it again. Sometimes you don't want to completely stop the program. You just want to suspend it momentarily until something is resolved. Then you say, hey, if that index is 1, then go ahead and halt it or hold it. There is another command called hold, which does something similar. You can temporarily suspend the program instead of ending the program. And then you can say end of select. Do you see that? So it's like the if that had end if, then this one also has end select. Okay, so these conditionals, they need to end if and end select. Okay, and so we learned the command stop and halt and select case and select. Let's move. Now, can you define create and call a user defined function? Can you do that? The answer is yes, you can. How? The way to do it is using the word program. So program can be used to create the main function or the main routine, as well as any basically user defined function. So what would you do? You say program turn on output. So this is a user defined function. What does it do? It basically goes with the some pin output and turn it on, and then delay for 1 millisecond, and then it goes and turn it off. Okay, so that's all it does. Turn it on, 1 millisecond, turn it off. Now in your main program, what would you do? You say, hey, output number equals 3. What is this? This output number here is a global variable that you defined before your main program or your user-defined function. Okay, this is a global variable which can be used inside your user-defined function. And that is a pin number in this case, or a port number. Why would you do that? Because in the standard PAC language, these user-defined functions, they cannot directly access parameters like traditional functions. So if you want to pass them data, you do it through global variables, which are defined using the keyword var. So whenever you see var, it means a global variable. Or they can be done with, for instance, a position variable or an integer or anything like that. So this global variable, pin 3, is now sent to this program to be turned on, stay 1 millisecond, delay, and then off. And once that happens, then take arm, do something, and give arm an end. Now look here. How would you call that program with this pin number to turn it on, stay for 1 millisecond, and turn it off? The way that you call a user-defined function is using the keyword call. So you create it using program and you call it using call. Okay, when you call it, this is like running it. Okay, and we know we always call functions in any language, and that is exactly what you're doing here. So this is calling and creating and calling a user-defined functions. Now there is another thing that we need to talk about, and that is called subroutine. How would you create a subroutine and how would you call a subroutine? So what is a subroutine? A subroutine is a lower level flow control. It's like a local function that can only be used within a single program, cannot be accessed and called from other programs, and it does not support access to the parameters via those global variables. Okay, so it's much more limited compared to a user-defined function. When you want to create a subroutine, you typically give it a name and then you start by a column, and then the commands that need to be executed within that subroutine or by that subroutine are immediately followed after the column, and then to return back from that subroutine to the calling program, you will use the keyword return. So here in program main, you say go to sub init, which is an initialization, do some stuff, end. So you see, I create them, as I said, by typing their name, column, their commands they need to execute, and a return. And when I want to call them and execute them, I use the command go sub, followed by the names. Okay, and they are used within their own program. And if you remember in the beginning of this video, I said that when you have the keyword end at the end of a program, that's where the subroutines start. And you see this subroutine started after the keyword end. So end does not mean the program ended. It means the motion inside the program ended. The subroutines of the program will be defined underneath after the keyword end. Okay, so this is how to create a subroutine, user-defined functions, and finally we have go-to. So go-to is when you want to jump from one part of the program to another part. Typically, you have checked some condition, and based on that condition, you want to go back and execute something like a loop or something. And this is basically a replacement for loops. Most of advanced programmers do not like the idea of goto because it can easily confuse people, and they always prefer using for loops or while loops and if conditions, but goto is kind of a replacement for them, but not a professional one. And so here I'm going to show you that. I also show you how to look into an error. If some error happens, then based on that error, you catch whether an error happens, and if it happened, then you do something. So here I want to show you both go to and jump around the program, and I want to do an error function. So what do we have? We say in program main, define some int tries, okay? And then tries equals 0. By the way, this command int is different from def int that we had when you wanted to initiate and start an integer variable. This int is a little bit different. If you want to know, you can always go to this manual and look it up, and you can see that int basically, it says it returns the maximum integer that is below that value. So if you pass the 123.456 to it, the output is going to be just 123. So this is like the ceiling command that you had in programming, okay? So, but anyways, that is going to be an integer number. So you started with 0, And then here, look, that's your subroutine retry. What is that? You're gonna add 1 to this tries, and you start the system, and then you check the command error number. What is error number? The error number or error no command, it basically returns an integer for you whenever some command fails or produces a warning. So if you try to do something and the compiler returns an error or a warning, that error number will be an integer not equal to 0. If it returns a 0, that means no error has occurred. If it's not equal to 0, that means some error has happened. And you see here, if you want to check not equal, you have to use this operator. In PAC, this means not equal, okay? So you said if some error happened, then print. So this is going to print it to the output of the system. Error, try again. And if the number of tries is less than 3, then go back to here. So what does this do basically? It tries to do something, and if that thing, it 3 times try to do it, and each time if it doesn't happen, tries again until it gets to 3. If 3 failures back to back happens, then what does it do? Then it says, hey, failed 3 times, I'm gonna stop. How does it stop? Okay, so you see that basically this is that end here, right? That is going to end the subroutine, end if and end of the other if, then proceed with the rest of the logic, give arm and end. So the subroutine, which is coming back to itself and repeating itself, is going to only try for 3 times. And if it doesn't work, then it ends the subroutine. So this end here is end of subroutine. And you see, basically, any time that failure happens, this line will bring the control. Instead of going to here, it doesn't. It comes back to the beginning and start again. So you're creating a loop here. Okay? So again, it creates a loop, and that's not the best way to create a loop. So I recommend against this. As with any other programmers, they are no fan of goto, but know that this command exists. And if you want to know exactly what does the command print do, again, remember, we can always go back and see when we say print something, where does it actually print, huh? So here, look, that's the command print. And you see, it outputs the data from the RS-232 connection or to the Ethernet port. So it's not going to show it on the screen. It is going to show that. It is going to send it out from the output port, the Ethernet port or the RS-232C port. Okay, it is not going to show it on the screen. If you want to show something on the screen, a screen of what? A screen of the pendant, this guy here. If you want to show a message over there, there is a separate command for that. And what command is it? That's this command here, print message. Okay, so if you want to send a message on the LCD of the teach pendant, then use the command print message. Okay, so if you say print message hello world, that is going to be shown on the pendant. So print is going to send it to RS-32 or Ethernet port, just so you know. So hopefully this relatively long video told you enough about how to program in the PAC language. I know I have not gone over all of the commands, and that's not my goal. You can always refer to this PAC reference, which I'm going to give you a download link on the video description. And you can also download it from the Denso website themselves. This is your full guide if you want to know how to write any command and the syntax for them, and lots of other useful information. So you can always come and look at this file. That is your best friend. Okay, it has lots of things in it. And the goal here was just to introduce the basics to you. So in my future videos, when I do some task with Denso robots and I show you the code, you understand what is it that I'm doing. Thank you so much, and I'll see you in the next video.